So, welcome back student to the next class of complex analysis. So, today we will learn, so in the previous class we know how to calculate the residue and all these things. Today we will going something interesting which is called Cauchy's residue theorem. Cauchy's residue theorem. So, this Cauchy's residue theorem that this is not a very new thing to you, because I have mentioned that these things in the previous few classes. So, let me again give you the what is the meaning of these things and what is the statement of this theorem. So, if say this is a region D and which is bounded by a simple curve C. So, C is a simple curve which is bounding a region D where the function f z is analytic. So, f z is a function which is a function f z is a analytic in the region bounded by the simple curve or contour C, except few finite points say Z1, Z2, Zn. So, first try to understand what is f z is analytic in the region bounded by a simple curve C except few finite points say Z1, Z2, Zn. So, that means it is not entirely analytic in the region. There are few points, I mentioned this point like this here, 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 this is say Z1, Z2 and so on. So, these few points Z1, Z2, general point Zi and Zn, there are n points here suppose where the function is failed to analytic. That means, these are the region, in this region the function is analytic except at this particular points, and these points are finite. In that case, if that is the case, I know that if I make a circle around here, if I make a circle around here, if I make a circle around here, and if I make circle around here, I can write the closed integral of f z over this region as this is say C1, this is C2, this is Ci, this is Cn, this I is a general element. So, I just write this as the summation of this quantity. This we have already proved in our previous class. So, I am not going to prove it once again. I just encircle these things and then it become a multiply connected, and for multiply connected this is true. I just cut out these things, and then if I add, then I will get these things. This, if I write in summation form, it will be look something like this: summation of Ci I goes to 1 to n f z dz. So, this is the first statement, and second I can write this in this form. And what about these things? What about these things? This is I need to erase these things first. Then I can write, so let me first complete the statement, then I am going to prove. Then this quantity, which is summation of this, which is summation of this will be simply 2 pi I summation of the residue of the function f evaluated at I point with summation which is 1 to n. This is the statement. So, let me understand. So, let us understand once again. So, we have a region which is bounded by some curve C, the region D is bounded by some simple curve C. The function is analytic except this point. So, these points are singular points. First, I have already mentioned that this function is singular point. If the singular point is present, even then I can able to evaluate the total integration of that. Please remember one thing, if there is no singular point here, that means the residue is 0, then I have the entire region the function was analytic, and I know that if the function is analytic some region, closed integral in that region bounded by C will be 0, that I know. This is Cauchy's integral formula is this, Cauchy-Gaussard theorem is this rather. So, now I am saying that fz is not entirely analytic in this region, there are finite points where fz is failed to be analytic. Then what happened, that I can write this as 2 pi I and the residue, because this function should have some residue here, because these points are singular points, and residue I calculate that a function is given, there are few residues are associated with that. If I able to calculate the residue, then I will just add these residues, because here how many singularities are there, n number singularities are there. So, I should have n residues. So, I will just add this n residues multiplied by 2 pi I and I will get the result. Why this residues is coming in number? Because my integral is now divided into n part, 1, 2, 3, 4, 5, 6 up to n, C1, Ci goes to n. So, that is why this integration is coming to n part. So, for each integration I will have one residue, and this residue is add up with this, and 2 pi I term will come. Why it is coming? So, now let us try to understand that. So, statement is quite straightforward, that if a function is analytic except this point, then if I want to find out the closed integral over that region, then I will have something 2 pi I summation of residue. Okay. So, now let us go back to our Laurer series expansion. So, in Laurer series expansion, I have this expansion in my hand, and this is valid for when, if we have some kind of singularities here, then this function is bounded, this function was in some annular region. For example, this expansion, if you remember, was for small r to big R. So, there was some restriction for which I can expand this function. So, at z equal to z0, what happened, this function is, say, z0 points are nothing but z1, z2, zy and zn. So, around that I am expanding the function around these singular points. If I do that, then I can have several points, the old expansion that we have already done, minus a minus k plus 1 z minus z0, the usual thing that we have already encountered, plus one important a minus 1 z minus z0, and then the analytic part a0 plus a1 z minus z0 and so on. Several time I am writing this so that you can aware of this thing, But the important thing is that what is the value of a k? The value of a k, if you remember, I have was 1 by 2 pi I integration of f z z minus z 0 k plus 1 dk. That was the value of a k. So, once I have the value of a k in my hand, so what I can do? I can put the value of k. So, for k equal to minus 1, for this special k, what I will get a minus 1 is equal to 1 divided by 2 pi I integration f of z dz, because k is minus 1, that means this term will going to vanish. So, only thing that is in my hand is the integration of f z dz, and integration of f z dz is two pi I multiplied by a minus 1. Now, this a minus 1, this a minus 1 is nothing but the residue. So, I can rewrite this expression, let me erase this. So, I can rewrite this expression as this. So, two pi I residue of this function at that point z0 where the function is. Now, if instead of one residue, if instead of one singularity, if I have many singularities, then this will be sum over that. So, 2 pi I sum over residue of f z of f at z I 1 to n, which is essentially the expression that I have written in the previous just few minutes ago. So, now we have the expression in our hand, which suggests how I can evaluate a closed integral f z. If the residue is known, then I can calculate the closed integration. Please remember, if there is no singularity, then the function is entirely analytic. If the function is entirely analytic, if you take a closed integral, it will give you 0, because it is a path independent. So, now we will going to exploit this this expression or this theory and evaluate some problems. Now, this is the interesting part, how to execute this theory to solve a problem. So, let us take few examples or few problems. So, what examples we have first? So, examples 1 or problem 1. We will do several problems related to this, because this is a very important theory that we just show. So, the function integration that is given to us is this z plus 6 z square plus 4 dz. I need to evaluate this integration, but I need to know for which region I am doing this. The region that is given is z minus I is equal to 2. Okay. So, this is the function, this is the region. First, I need to identify which region, at which region I am evaluating this. So, z minus 1, z minus I means the origin is at I point, and I should have a circle with radius 2. So, if I have a circle of radius 2, so the region, so this is 0, this is I. So, I will have a circle like this, something like this, where this radius is 2, this is 2, this is 2, every place is 2. So, now this is the function. So, I need to find out for this function z plus 2i z minus 2i. The function is written in this way. I simplify this. So, that means there are two singularities are there essentially at say z1 is one singularity which is as minus 2i, and z2 is another singularity which is at 0.2i. These two singularity I have, these are the singular points. Singular points. Next thing is to check which points is inside here, both are here, both are outside, or both are inside, or one is inside, one is outside. So, let us try to find out. So, let us locate what is minus 2i. So, if you remember, this was I, this point was minus I, and minus 2i is below that somewhere here. So, this point is minus 2i. So, minus 2i is outside. I should not bother about that. So, this singularity, this singular point is outside the region where I am trying to evolve. So, now this is I, this point is 2i. Obviously, the point 2i is inside the region. So, point 2i is inside. So, this point is inside, and this point is outside. I should not bother about the point outside, because this point will not going to have any effect on the integration. Only thing I need to bother about this point. So, now I can evaluate this. So, function of f z, I can write simply, okay, let me directly do the problem, because I know where the singularity is. So, okay. So, what should be the result of these things? What is the formula? The formula is closed integral f z dz will be, this closed C is this one, what is given here, say this is C, this C. So, if I integrate this over this region, then what I will get? I will get 2 pi I and residue, summation of residue. But here we have only one point that is singular. So, we do not need to put this summation sign here, just one point is there. So, just at that point the residue will be enough. So, residue of the function f at which point? At which point? At 2i point. So, let us put 2i here. So, only thing I need to evaluate is this quantity, which is easy. So, let me just try to find out how the residue one can find. If 2i is limit z tends to 2i, z minus 2i will be multiplied by the function z plus 6 divided by z minus 2i z plus 2i. So, z minus 2i will cancel out, and then if I put the limit, that will be the result of the residue. So, now 2i, if I put, it will be 2i plus 6, and the downstairs it should be 4i, here 2i plus 2i, so 4i. So, this whatever the value I have, this is my residue. So, now the result is 2 pi I multiplied by the residue. So, I will need to multiply this quantity with the 2 pi I to get the full result. So, if I do, then I will have 2 I plus 6 multiplied by 4 I, or if I take 2 common here, this 4 will cancel out. So, pi, this I will cancel out here, and if I take 2 common here, then this 4 will cancel out. So, pi, it seems to be pi I plus 3. So, that is the result, that is the result I am looking for. So, this is the value of the integration, the complex integration in the region where we have singularities, but one singularity is outside, and if I calculate, the residue is comes out to be this. I just put 2 pi I multiplied by summation of residue. Since one residue is here, so I just calculate this and find this result. but please mind it, if the region is changed, for example, if it is say 5 or 6, then this radius will be bigger than this. Then this 2i point will be included, and you need to calculate for this 2i point also, if the region is changed. So, obviously, it will be depending on the region. If this region is changed to half, for example, then both the residue is outside, both the singular point is outside, it will be something like this. So, inside that there is no singularity, the function value of this integration will be 0 then. So, that means the value of the integration is mainly depend on the region that is given to you. If the region is changing, then you will have different result in each cases. Okay. After that, we will go to more examples, because there are few examples are there we need to cover, which is important. So, let us go to my problem 2. Problem 2. So, in problem 2 we have something like this. It is given as 1 divided by z square plus 4z plus 13. This is the expression I have in my hand, but I need to mention also what is the region here. The region is given as z, the c, the contour is as z minus 3i, z minus 3i mod of these things is equal to 3. So, first we should be very careful about the region, and then find out whether these singularities, obviously this function have some singularities. So, first let us check where the region is. So, z minus 3i. So, the point 3i minus 3i point is somewhere here. So, if this is 1i, 2i, 3i is somewhere here. So, this is 3i point, and I am taking a radius, taking a circle of radius 3. So, that means it will cut to 0 point and then go up here. So, it will be something like this. So, this is the region where I need to, this will be in the middle of the circle, and this is 3, this is 3, the radius is 3. Okay. The region I know, understand. The next thing is that to evaluate. So, z square plus 4z plus 13, this quantity where it is 0, we will have the singularity, that is for sure. So, this quantity, if I write z minus z1 and z minus z2 equal to 0, then z1 and z2 will be the two solution of these things, this quadratic equation, which we know how to solve. So, z1 is minus b plus root over of b square, that means 16 minus 4 AC, 4 AC. So, 4 into 13 divided by 2. So, here we have minus 4 plus root over of, this seems to be 16 minus 52, 52 minus 16 is seems to be 36, minus of 36. So, state where I am writing this, it is minus of 36 divided by 2, divided by 2. So, this quantity is minus of 2 plus, if I take 36 out and take I as root over. So, I will be here because root over of minus 1 is here, 36 out, it will be 6 and divided by. So, it will be like minus 2 plus I3, Z1 is my minus 2 plus I3. We know that if we have a complex root of a quadratic equation, then if one root is this, the other root must be the complex conjugate of that. So, Z2 I am not going to evaluate that, is minus 2 minus I3. So, Z1 and Z2 I evaluate. So, let me write it here somewhere. My Z1 is minus 2 plus I3 and Z2 is minus 2 minus I3. These 2 points I have. So, once I have these 2 points, then I need to consider whether these 2 points, which of these points are inside and which of this point is outside. So, you can readily find which point. So, it is minus 2, say Z2 point is minus 2 minus I3. What is the coordinate of this point? Minus 2 minus I3. So, minus 2 is somewhere here and minus I3 is somewhere here. So, that means this point seems to be outside, and other point, I should write it here, other point is minus 2 plus I by 3. So, minus 2 plus I by 3 is here and 2, so somewhere here. So, this is the mirror point of each other. So, it should be something here anyway. So, one point, so this is my Z1 point, this point is my Z1 point and this 2 is Z2 point. So, again I find that Z2 point is outside, Z1 is inside. Since Z2 is outside, I should not bother about Z2 point, I should only think about Z1 point, and then this result I am kind directly write 2 pi I residue, because the result I now evaluate function of Z and the residue at the point Z1, because Z1 is inside. So, I need to figure out what is this now. So, residue of Z1 is how much? Limit. So, residue of fz Z1 is limit Z tends to Z1, I multiply Z minus Z1 with the function which is this. So, 1 divided by Z minus Z1 Z minus Z2, this term will cancel out. Now, I put this here. So, I will eventually have 1 divided by Z1 minus Z2, this is my residue. So, what is my Z1 minus Z2? If I, so Z1 minus Z2 from here is seems to be 6 of I. Now, I just put the value here 6 of I and I am done. So, residue I figure out it is 6 of I. So, 1 by 6 of I rather, 1 divided by 6 of I. So, 1 divided by 6 of I is I will cancel out. So, it should be something like pi by 3. It seems to be something like pi by 3. So, we find the value of this quantity, this integration pi by 3. So, we should not have calculate the point at z equal to 0, as I mentioned this is outside, but if the radius is somewhere bigger which include this Z2 point, then we need to take care of Z2 point also. So, here I like to stop my class. So, in the next class we go on with that. There are merely 2 examples I show, there are few other examples. So, I will invest more time in solving different problems and try to find out how you calculate the integration by using this Cauchy's residue theorem, which is important, and cover as much as possible different kind of problems with the different kind of problems. With this note, let me conclude the class here. In the next class, we will go on with this, we do more problems, and till then have a good day and thank you for your attention.